Welcome back to my YouTube channel. This is a part 2 of 2 for SPM Physics from 5 Chapter 3 Transformer. Previous video, I've gone through with you how do you find out the efficiency where power unit watt. W capital. Okay, so this is what we've gone through. I hope you have at least gone through at least 30 objective questions or multiple choice question, at least 30 questions on calculation, on how to find out the winding, number of winding, or perhaps the output secondary voltage, or in some cases they ask for the efficiency. Okay, so this is we are not going to go through that because I presume you have made use of the past one whole week. You have used about 1 week time to finish at least 30 questions, objective multiple choice question. So this this video, I'm going to go through with you the what are the factors, okay, affecting the efficiency. Okay, what are the factors? There are actually 4 factors. First factor, like what you have in the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in diagram, in some, I think you are quite familiar now. So in some question, they will have a diagram look like this. You have more winding, and then maybe 1, 2, 3, 4, 5 winding here. Obviously, this is a step down transformer, and here it has to be a sinusoidal input. This is your V primary, and then here would be your output secondary. You do not expect to work under battery. Okay, it doesn't work because you need to have a change in magnetic field, Lenz's law, so that you have an induced current over the secondary coil. Okay, so this is what we have gone through in the past. So what are the factors affecting the output? Here, this is the output to be low. There's some loss of energy, of heat. What causes the heat loss? Okay, first factor goes to the wiring. Okay, first factor go to the wiring. So this is called the resistance. Now you should have your reference text. It helps you to read your reference text. Resistance of coil. First factor. Okay, in order for you to reduce this loss energy, okay, as heat loss, heat energy, the resistance of coil has to be reduced. One way to do that, it will be you use a thick copper wire. A thick copper wire. From what we learned in our previous chapter, in my video also we mentioned that resistance, when you have a big cross-sectional wiring, then electron will be flow through it faster, therefore it reduces. A thick copper wire, so therefore it reduces the resistance. Okay, so the resistance of copper wire has to be reduced. That's the first law. Just to refresh your mind, resistance R is equals to resistivity, length over cross-sectional area. You have the wiring, right? This is wiring. You have a big cross-section area. more electron will be able to flow through it. Therefore, when the area increase, therefore the resistance reduce. So this is what we have learned in the past. So first, you need to reduce the resistance of the coil. Second factor, this is the coil. Second factor, the middle part. We call the magnetization and the reversal of magnetization. Okay, that's the second factor. Okay, the use of soft core iron. Okay, use soft iron core. Okay, I want to find out what are the factors to increase the efficiency. First, you reduce the resistance. Second, you use soft core iron. Why is that so? If you go to the soft core iron, it's capable to magnetize, easily magnetize, and demagnetize. How is that so? Now, this happens when we have first half cycle, you magnetize it. Say for example, in the first half cycle, you magnetize the coil. During the next half cycle, the same coil, the direction has to go down. So, magnetize and demagnetization use up energy. Okay? The reversal, so you want to use a material which is a soft core iron, which is easily magnetized and demagnetized, so that less heat energy. The keyword is heat energy. So that less heat energy is being converted. During the reversal. Okay, so this is something that you can't see, but that's the benefit of for using soft core iron. The second point. Third factor, you have the coil, you have the iron core. Now the third one is also related to the iron core. You use, how are you going to do that? In order to do that, you use laminar. You use laminated meaning layer, laminated iron core. Okay, instead of a piece of metal, solid block of metal, instead of using a block of metal, all you need to do is you replace it with pieces, thin sheets of it. Okay, you compound them. Okay, why do you need to use laminated laminated often, you use laminated iron core to reduce eddy current. Now, eddy current came out in SPM 2007. So, well, so it shows the importance of eddy current. Okay, it's not good. Eddy current is not good. You use laminated iron core to reduce eddy current generated in the iron core. Why there is this eddy current generated in this iron core is because during the process of magnetized and demagnetization, this iron core itself would have electron. Okay, so therefore it would produce a current, and the current produced in the core is eddy current. So therefore this eddy current generated will be converted to heat energy by P equals to I squared R. In this case, this is the eddy current. Okay, in order to reduce it, use laminated iron core that insulate sheets of iron. How? This laminated iron core insulate the sheets, because each sheets of this iron core is being painted with enamel paint. So it insulates the sheets to increase its resistance. Increase the resistance so that the current can't really flow. It's just that we have very high resistance to the flow. Of eddy current. So therefore, energy loss is reduced. This is a crucial one. This is quite important. Why do you need to use laminated iron core? Okay, and iron core is to reduce eddy current in the iron core. How you do that? You use laminated sheets. You paint it with insulator so that eddy current generated can't flow around here. And if that's very little amount of eddy current flows around here, what happens? Energy loss is reduced. This is the heat loss, heat energy loss. Okay, that's the third factor. The last factor, there are only 4 factors. The last factor is you need to reduce the leakage. Reduce the leakage. KAG, leakage of magnetic flux. Okay, leakage. One way in doing so the iron core you use, the iron core should be in a closed loop. So this is an example, like say for example, if you have the iron core to be in U shape, okay, then you wind around your primary and then you wind around secondary. What happened here, there's a leakage. There's a leakage of flux generated by, generated by the coil. So in order to reduce the leakage, what you do is a closed loop. It will be either a square where you have your primary coil and secondary coil. Here you have a joining because you can't make a square, so you get a U and then it has to be joined, a closed loop. Or you wind them together. You wind the primary coil and secondary, and then wind it over like in a T shape. Primary, you have a coil, primary, and then followed by the secondary. Okay, you doesn't need to worry the copper would short circuit because the wire itself will have an enamel. We have enamel paint, so it's actually isolated. So you wind them together. Where this is not an I-beam. Here and then maybe you have the closed loop. Okay, you close them. In some transformer, they're winding in the center. Okay. So 4 factors. First would be reduce the resistance of the coil by using a thick copper wire. Second factor would be to use soft iron core because it's easily magnetized and demagnetized, so less heat energy is being converted during the reversal of magnetization. Then third, they are also related. You use laminated iron core is to reduce eddy current. Okay, to do that, you insulate these iron core sheets to increase the resistance. So the flow of eddy current is reduced, and therefore heat energy loss is reduced. And the last factor would be to reduce the leakage of the magnetic flux by having a closed loop of iron core, or the both primary and secondary coil should be wound together closely to prevent a leakage of magnetic flux. So that's basically all about it on a transformer. Now, just in case that I worry that my previous video is insufficient in helping you solve problems, here I also want to include one question, objective question, just in case you have faced it, you have no idea how to solve it. So let me try one example with you together with the previous example, because previously I've gone through how to find the efficiency using power, but I believe I haven't gone through the number of winding. Yes, question relates to number of winding. So let's convert it into a diagram. Says it's a box diagram, in and out, input output. Normally when you have a question, then you will try to put into input and output in this manner. It helps you to solve it better solve one questions. Okay, says the voltage of supply is 240 and the efficiency is 96%. Okay, to power, let's say 2 bulb, you have 2 light bulb, maybe 1, 2. The never-tell is parallel. Okay, I've drawn it not right. Maybe you want to power in a parallel light bulb. Okay, one side, another side is out. 12 watt, 24 watt each. They find what is the number of winding over the secondary. If the number of the primary given number of primary is 900. So for this, it's quite straightforward because from what we have gone through in the experimental data, paper 3 normally. Here, how to make use of this? Vs is direct proportional to Ns. Secondary, we talk about secondary, it's all about output. So for this kind of question, first Vs over V primary is actually Ns over Np. Since this is what you need to look for, you always start out with an equation, and then from the equation, then you were able to find out which one to use. So this is what you need, so therefore you rearrange them. P times Np. I know what is Vs, I know what is Vp, so therefore my secondary winding, secondary voltage is 12 over primary is 240 times primary is 900, unit is winding turns, so therefore your secondary winding, put in a calculator, it's 45 turns. Okay, so that's first type question. Second type, the current in primary coil, so that the light bulb is lit on. Okay, normally lit on. So in order to solve this kind of question, you seems like clueless, but look at the question again. They give you efficiency. So efficiency is P output over P input times 100%. Okay, so they ask for the primary, meaning the input, and from power, when P equals to IV, so from here you're able to find out what's the current. So therefore 96 is equals to output, I output, V output over I input, V input times 100%. So I need to know what is the primary, so what is the input, right? So bring it up, so therefore input would be output current where is my output current? So here will be a bit tricky because here when secondary current comes in at a point, what happened? When the current reach a point parallel from my previous video, they split, isn't it? The current split into half. No, since they are the same, so split into half. So one is 24, another, this is 24, so therefore you would expect it to be 48. So here eventually it's 48, it's not 24 because it's parallel over 96 times 240 input times ordinary 100, and therefore the answer should be 0.21 ampere. Okay. The tricky part is why is it 48, right? Because it says only 24. But this is parallel. When current reach a point in parallel, what happened? They're split into two rods, 1 and 2, become I1 and I2. At a point, they're split. So 24. So the total current here should be 48 watt. I mean, the total power is 48 watt. Right? I think if you understand this already, I think it will help you to answer at least another 20 more questions for this week. Normally 1 week, 1 video. And if you're watching first time watching my video, kindly subscribe to my channel. It's free. And I really appreciate those thumbs up button. Until then, stay tuned to my next video. Thank you.